All right, so here we've got chapter 9, problem number 73. They say Joey from example 9.10 stands at rest at the outer edge of the frictionless merry-go-round of figure 9.28. The merry-go-round is also at rest. Joey then begins to run around the perimeter of the merry-go-round, finally reaching constant speed, measured relative to the ground of 5 meters per second. What is the final angular speed of the merry-go-round? So here we've got our merry-go-round, and it spins around and around and around in a circle. Joey should be on the merry-go-round. You know what? Let's put him on the merry-go-round. That way it looks a little better. Joey's very happy to be at the park playing, running around the merry-go-round. All right, so there he is running around. And he's running in a direction, right? And then he's causing the merry-go-round to spin. Because of all of this, our object is going to start rotating, and we know that angular momentum needs to be conserved. So we can say that L dot sub I is equal to L sub F. All right? And this L then becomes the sum of the angular momentums for momenta for both objects, for the merry-go-round and for Joey. So the merry-go-round has its own I omega term, right? And Joey also has his own I omega term. And that has to be equal to the finals on the other side. Okay. So looking at this, initially they say it's at rest. Right? Joey and the merry-go-round are at rest, so those go away. So we're left then with 0 is going to be equal to the moment of inertia of the merry-go-round and the angular momentum of the merry-go-round and the angular momentum of Joey. So if we kind of expand this out now, the disk has a moment of inertia of 1/2 mr squared times omega sub f for the merry-go-round, and we can treat Joey as a point mass of mr squared times his final angular velocity. Okay, bringing things over to the other side, right? We'll bring the disk over to the other side, the angular momentum of the disk over to the other side. We'd have 1/2 an m of 200 with a radius of 2 squared, right? And that would be times the final rotational speed of the merry-go-round. And that's going to be equal to Joey's moment of inertia of 36 times 2 squared. And then his angular velocity comes from the relationship we've seen that the linear velocity is equal to the angular velocity times the radius. So solving for that, we can plug in that would be v over r, which would be 5 divided by 2. Right, so a couple 2's cancel out, and we'd get then negative 400 omega sub f for the merry-go-round is equal to 360. All right, so that means then that the final angular speed for the merry-go-round is going to be, let me fix that, negative 0.9 radians per second. Now, it seems odd that we would have a negative angular velocity, but if you think about it, it makes sense. We need angular momentum to be conserved, and if we start with 0 before Joey starts to run, right, we need to have 0 angular momentum after Joey starts to run. So if Joey's running at this 5 meters per second in one direction, we need the merry-go-round to rotate in the opposite direction to counteract his angular momentum so that the total system is still 0. So again, if he's positive 5, whatever that ends up being, omega 5 divided by 2, well then the merry-go-round needs to have a negative 1 again to balance out his angular momentum. All right, so that is chapter 9 from our book, problem number 73.